As we all know that during the course of the reaction, the concentration of the reactants goes on decreasing and the concentration of the product goes on increasing. So we had just understood at time t is equal to 0, that is at the start of the reaction, the concentration of the reactants will be more. As the time proceeds, the concentration of the reactant goes on decreasing and the concentration of the products goes on increasing. Now if you want to study how it varies graphically, so graphical representation of the rate of the reaction can be understood by this nature of graph. So if you plot a graph of concentration of the reactants over time, so concentration of the reactants, I have taken it on y-axis and time I have taken it on x-axis. So if you see, concentration of the reactant goes on decreasing. So you can see concentration of the reactant goes on decreasing with the increase in time. So at time t is equal to 0 at the start of the reaction, if I say the concentration is 4. After 1 second, concentration is decreased to 3. After 2 seconds, concentration is decreased to 2. So if you study, the concentration of the reactant goes on decreasing with respect to time. So if you want to study graphical representation of concentration of products versus time, so you can see that concentration of the products goes on increasing with the increase in time. As the reaction proceeds, the concentration of the products goes on increasing. So if you consider units of a rate of a reaction, so we all know that rate is equal to concentration over time. So change in concentration of the reactants or the products over time. So if concentration is expressed in terms of moles per liter and time in seconds, then the unit of the rate of the reaction will be moles per liter per second. For gaseous reactions, if you consider, so whenever there is a gaseous reaction, then the concentration is expressed in terms of partial pressures. Then the unit of the rate of the reaction will be atmosphere per second. So this is for gaseous reactions. So let us understand what is average and instantaneous rate. So average rate is nothing but rate which is measured over a long time interval. Okay, so average rate is represented by delta x upon delta t, or delta x. X is the concentration of the reactant or the product. Okay, so delta t. So delta here, this delta refers to large change. So delta t refers to large interval of time. Okay, so average rate is that rate which is measured over a long time interval. Now instantaneous rate, if you consider, represented by small d here. So d here refers to a small interval of time, small change. So dt is small interval of time. So whenever a rate is measured over a very small interval of time, or a rate which is measured at a particular instant, then we refer it to as a instantaneous rate. So average rate is measured over a long time interval. Instantaneous rate is measured over a very small interval of time. Okay, so always you remember that instantaneous rate is more practical than average rate. Okay, it is determined graphically by measuring the slope of the tangent that is drawn at a particular point. Okay, so if you represent it graphically, so you are supposed to carry out the rate at particular instant. If you want to carry out particular instant of time, so at particular instant of time, if you want to find out the instantaneous rate, then you are supposed to draw a tangent and then find out the slope. So slope of the tangent that is drawn at a point that will given at a particular instant, that refers to your instantaneous rate. Moving on to next part, that is expressing for rate of the reaction having coefficients. Okay, so if you consider a reaction A moles of A reacting with B moles of B to give C moles of C and D moles of D. Now here the coefficients are small a, B, C, D are said to be the coefficients. Okay, so how do you express the rate of the reaction having coefficients? So here the rate of the reactions in which the stoichiometric coefficients of the reactants and the products are not equal to 1, then the rate term of each reactant and the product is divided by the stoichiometric coefficients. Okay, so what is done here, whenever the coefficients are not equal to 1, what you are supposed to do is the rate term of the each reactant and the product should be divided by the stoichiometric coefficient. Now how will I write? Rate is equal to, now for this reactant A, if you want to consider, so what is the rate equation for this? Delta A over delta T. So I should divide it by stoichiometric coefficient, that is stoichiometric coefficient for A is here small a. So 1 upon A. So minus I am writing it here because it is the reactant. So for reactants I will have to write the minus sign. So is equal to minus 1 upon B. 1 upon B is the stoichiometric coefficient. B is the stoichiometric coefficient. So I have written minus 1 upon B. Change in concentration of B over change in time is equal to 1 upon C. Okay, C is the stoichiometric coefficient over change in molar concentration of C over delta T is equal to 1 upon D, change in molar concentration of D over change in time. Now for the product side I have not written minus sign. So only at the reactant side I am supposed to write the negative sign here. Okay, so if you consider a reaction between hydrogen and iodine, hydrogen plus iodine to give Hi. So how will I write? So here stoichiometric coefficient is 1. So I need not have to write it. I'll just write minus, because it is the reactant, change in concentration of hydrogen over delta T is equal to, here also the stoichiometric coefficient is 1. So change in concentration of iodine over change in time is equal to, now here the stoichiometric coefficient is 2. So I should write 1 upon 2, change in concentration of Hi over change in time. So if I want to write gaseous reaction expressed in terms of partial pressures, okay, so whenever you have a gaseous reaction, so that you can also replace concentration by partial pressure of the reactant and products, and we all know that partial pressures are said to be directly proportional to concentration. Okay, so I can just write, so if you consider one more reaction which is also a gaseous reaction, nitrogen plus 3 hydrogen reacting to give 2 ammonia. So here reactant is nitrogen, so minus change in partial pressure. So instead of concentration, instead of square bracket, I am writing it as P. P here refers to partial pressure of nitrogen divided by change in time is equal to minus, so stoichiometric coefficient is 3. So 1 upon 3, change in partial pressure of hydrogen over delta T is equal to stoichiometric coefficient is 2. 1 upon 2, change in partial pressure of ammonia divided by delta T.